So we will start today's class with the nomenclature that we are going to follow for this course. I should have done it last class, slipped out. Our main quantity of interest is concentration, and we are looking at mass concentration. So the mass concentration symbol is rho, it is rho of A, and in some medium. So it is a concentration of A in water, air or some such medium. So here I have indices for I have to put some number here to indicate whether there is something here to indicate whether it is air or water. So I will have I here, I equals 1 is air, I equals 2 is water. The symbol 3 corresponds to solid and 4 corresponds to pure chemical. This is the general nomenclature. So if I write rho A1, it is so rho is itself rho of A is mass by volume. It is a density unit, mass concentration or density. Rho is a symbol for density anyway. In chemical engineering terminologies, we use C. C is concentration in terms of moles per meter cube, that is the convention. When we write rho, it is mass. So all our calculations will be in terms of mass. Rho is not convenient because our concentrations are all in mass per anyway. So whenever you go to the analysis sections, they are all mass per volume. So no moles per volume and all that, because we are not working at that range. Okay. So this is when we say concentration, it is by default in this class is mass concentration. In air, when we say rho A2, it is concentration of A in water. So what about soil? So in soil, you can also write rho A3, which is concentration of A on solid. But the problem is now this means we are looking at m of A divided by volume of solid. A lot of times volume of solid is not very easy to obtain. So if you take soil for instance, it's porous media, it is heterogeneous, different sizes. For me to get actual volume is very painful because of the properties of soil also, and it is laborious to do it. So instead we do not do this. We do this Ma over M3, this is the mass of the solid itself. So it is the mass fraction. So the mass fraction, the symbol is W or omega or W, whatever you can call it. This is this is mass fraction. We also call it as loading. WA3. So I also like to use dimensions instead of using units and all that. So we will call in terms of dimensions, rho A1 is Ma by L cubed. This L is 1 volume of air. Rho A2 is Ma by L cubed again. WA3 is Ma by M3. Okay. So in this context, when we apply this nomenclature to whatever we did in the last class, we had three physical properties. So the first one is aqueous solubility. We call it as rho A2, but we indicate that it is an equilibrium property by putting a star there. Okay. So whenever this star appears anywhere, it is something in equilibrium with something. It relates to equilibrium. Some mention of equilibrium is there. So it is the equilibrium of A with water, pure A with water. This is the equilibrium concentration of A in water. Similarly, vapor pressure is rho A 1 star. It is the equilibrium of A it is equilibrium concentration of A in air. So, yeah. And we also looked at Henry's constant. So, Henry's constant is a ratio, okay. So, it is a ratio, and we usually have this this partition constant kind of concept. So, this is a partition constant or a distribution constant.
Sir,
yeah.
What is the difference between rho A1 and rho A2?
Yeah, this one. So, rho A1 is concentration of a chemical in air, and that concentration of chemical in water, 2 is water. So, if you look at this, so you look at this rho A1 is concentration of A in air, and rho A2 is concentration of A in water, that is all. So, when you are representing a concentration of A in air, we write it as rho A1.
The mathematical formula is same, that we have written on right side.
No, rho A1 is I do not understand mathematical formula. It is just a representation.
We have written on right side,
yeah.
top of the right side.
Right. No, that is a dimension, that is a unit. The definition of that is mass by volume. So, I am writing this mass by volume is ma by L cubed, volume is L cubed, the dimension is L cubed. Ma is mass of A, and M3 is mass of the solid. So, mass of A over mass of solid. So, that is the definition and dimension of the terms that we are using. So, that is all, there is no other. So, this is the distribution constant also. So, we will give a generic term K, capital K. There is a lot of confusion, the small case, capital case and all, so you be careful. So, normally when you are writing a problem, you have to define whatever is that you are defining in words, so that there is no confusion. So, this is only for convenience. There are other symbols people, other textbooks use and all that. So, this is, I have found this to be the most, because there is a large number of interfacial things, this is the most unambiguous representation, but there are some textbooks which have evolved some other notation. So, they will use that. So, I am not contesting all that, there is no right or wrong way to do this. This is a matter of convenience and sometimes matter of convention. So, I would suggest that you do not get stuck with those definitions or those abbreviations. Okay. So, here we are representing the equilibrium of A between two phases, which means that both the phases have to come in this definition here. So, we are now talking about Henry's constant, we are talking about the partitioning of A between 1 and 2, 1 is air and 2 is water. If you write it like this and we put a star here, which means that it is an equilibrium quantity, it is a ratio of rho A1 to that of rho A2. So, both of these are in equilibrium with each other, that is already mentioned here. If you want, you can put a star sign here and a star sign here, both of them are in equilibrium with each other. That is whenever you put a star, it essentially denotes that this is in equilibrium with something. So, that is the easy notation for you to remember, so that later on when we write look at transport, this becomes easier for us to represent. Okay. So, this is a partition constant. So, I can write different partition constants. So, this is one, this is for air and water, this is we have air here and this is water. So, this is defined as a ratio. I put A 1 and 2, which means 1 goes to the numerator, 2 goes to the denominator. If I write this as Ka21 star, I will write it as rho 1 star. So, that is all. So, this makes it unambiguous, whatever the partition constant, however you define it, this is the way it is. Right. Any doubts in this? Any questions? So, sometimes you have this 4 pure chemical, whenever it comes we will discuss that. Sometimes it is there, we will look at it. In fact, aqueous solubility is like a partition constant between pure substance and water, or pure substance, saturated vapor is pure substance and vapor. So, you can write but ratio of we can't write in terms of concentration does not have any meaning there. So, it is pure phase, but sometimes when you write in terms of activity, people write that, people write activity in terms of 1 and all that. So, we will not get there, we will stay clear of that. So, we have now had properties of aqueous solubility, vapor pressure and Henry's constant. The fourth property that we are interested in is the partitioning of a chemical A between water and solid. By solids we mean soil or sediment or any such thing. Yeah. So we can write this in terms of we write it as Ka. I can write it as 3,2 arbitrarily. I can write it as 3,2. General convention is people write this Ka number as a ratio of things. So here if we are writing as K32, this will be WA3 over rho A2 because we are writing this in equilibrium of a chemical between water and solid. So it is the solid concentration. So do not worry about this star here, I am just putting it now here to indicate that it is in equilibrium, you do not have to put it all the time, just have to remember it, and if it makes it convenient you can put it, otherwise you know what it is, do not need to. Okay. So here if you look at it, the units here are again MA by M3 and this is MA by L cube. So the dimensions of this is L cube by M3. Unlike the Henry's constant, Henry's constant, both the units will cancel, so it will be some number, it is a ratio of concentrations, mass concentration. Here it is not so, L3 by M3, so it has units of meter cube per kilogram or some such thing. Okay. So now this is a general definition, this is partitioning of a chemical between water and the solids. So this is relevant, so when you are looking at soil water systems, for example you have groundwater, and you have water here, I think let me I'll just erase the entire thing. So I have water in the middle of the solids. Yeah. Suppose there is a chemical here. So we have a chemical here. We will call it is some chemical A. This will partition to the solid, between the solid and the thing. There is a ratio in which it will exist between this and the water, pore water. So this is the partitioning of and the solid. So the system is that static or moving slowly or whatever it is, do not worry about it right now, it is in equilibrium with it. So it is equilibrating between this point. So there is there are other solids sitting here on the surface somewhere, and the there is exchange between the pore water, chemical in the pore water and this. Why is this relevant? It is relevant because if you take the case of, if you take a scenario of say somebody, there is a soil, air, somebody dumps a large quantity of chemical on the soil, okay. We will put it as this is, somebody dumps a large quantity of chemical in the soil, and the so the chemical tries to go down, it goes down, it travels down by percolation, it's going in, and it goes all the way say to the groundwater, okay. The groundwater you have again this is groundwater. So this chemical is travelling So, this chemical is travelling all the way to groundwater, and depending on its property it will sit there, right. It was sitting here in the groundwater. What will happen immediately? This is a pure phase chemical sitting on groundwater. While it is sitting there, we will just focus on this first, do not worry about this part, we will come to that later. What will happen to this? What will happen to the chemical that is sitting in at that first sees the pore water? As soon as it comes in contact with pore water, what will start happening to the chemical? It will dissolve. It will dissolve into the water. When it dissolves into the water, it also comes in contact with the solid. So, when it dissolves into the water, it can also come in contact with solid. From the water, it can enter this, get accumulated on the solid, and it keeps happening as there is pure chemical being supplied from wherever, from the source, and it keeps accumulating on the solid till a point, just like solubility. At some point it cannot accumulate anymore, it reaches equilibrium between the concentration that is there in the pore water and the solids, okay. And then some point it will stop. This is how contamination of solids occur over a period of time, and then the reverse can happen. So, when there is a lot of there is chemical that is sitting here, and this chemical, there is some chemical here, and if this chemical leaves this place, there is a non-equilibrium that is set up, and chemical from solids will now get into pore water and then move away. So, this is the reverse of this thing, okay. All this takes a long time, we will come to all that later. It takes several decades sometimes to happen, for this to happen, because processes are very slow. For this reason, the partitioning of chemical between solid and water, pore water, becomes very important, very critical in terms of what happens, in terms of fate and transport of the chemical in the system, okay. So, if you are looking at the Ka32, this is Wa3 by rho A2. Now, we have two conditions, two possibilities here. One is for organic chemicals, this is true for organic or inorganic chemicals, either of these can partition, inorganic and organic both can partition. But a large amount of our discussion is organic chemicals. So, we will start with that first. So, organic chemicals, okay. So, if organic chemical is there in water and it is in contact with the solid, okay. This partitioning of organic chemical between this thing and solid. So, we now have to invoke what is the solid material. So, the one of these things is here now, if I want to measure, if I want to get the partition constant of any chemical here, suppose say I look at partition constant of a chemical in IIT versus partition constant of chemical in say Bangalore or Hyderabad or Delhi. What do you think the number will be? Will the number be different, same? I am talking about partition constant. Is Henry's constant, is it the same or different in different places? Henry's constant is it different in Chennai and in Delhi and Hyderabad? Our aqueous solubility is the same. What about Ka32 star? Same? How do you know? On what basis do you say that? This ratio of Ka32 star was Wa3 by rho A2, the ratio, the equilibrium ratio Ka32, on what basis are you saying that? If this is true, what else has to be true? Let us say that I take a soil sample from Marina Beach, the beach in a beach, and one soil sample from inside the campus here, and I put it, I make a solution of a chemical A, okay, and take one same solution A. So, I start with rho A to 0, I start with rho A to 0. In this case, I add beach soil, in this case I add forest soil, same concentration, same volume. Okay. When I put say 1 gram of beach soil and 1 gram of beach forest soil in both cases, and I shake it. At the end of some period of time, say 2 days or 3 days, how much of the chemical would you think would be on the soil in the case of the beach and the soil in the case of the forest? Which one would be higher? So, if I want to estimate WA3 here and WA3 here, which one do you think will be greater? Will they be the same? Do you understand the problem what I have posed? I have added the same amount of chemical in the water aqueous phase in the initially here, and I added the same amount of solid in both cases, but I have added different solids. One is from the beach, one is from the forest soil. You think it will be same or different? Why? Why will it be different? Huh? Properties of the soil are different. What properties of the soil are different, likely to be different? Porosity. Okay. Anything else?
Composition.
What composition? So, what is specifically in composition, what do you think will so if A is organic chemical, what do you think will be the factor, determining factor? Which one will be higher, this or this? From your general observation of beach soil, what is the difference between beach soil and the forest soil? One? No, soil. Let's check. I will go to a beach and take soil, and I go out and take. Water content may or may not be different. Is there anything else? Any other major compositional difference? Pores. Somebody said something? I couldn't hear. Any other difference? Big difference?
Loose.
Huh?
Beach soil will be loose.
Loose, okay. Now I can make this also loose. I can make this also like a property, this thing. Huh?
In forest there will be organic content.
There will be organic, more organic content. So, if you have organic content, that is a composition, one of the main these things is organic content for organic chemicals. You have to recall some discussion that we had earlier about organic matter itself. Now, which one of this will be greater? So, the organic content of a forest soil is higher. So, the organic content of a beach is less than the organic content of the forest soil. Now, the WA3, what do you think, how do you think it will behave?
More in beach soil.
It will be more in the, it will be more in the beach. Why? If organic content is less, why will it be more in the beach? So, if organic content is high, what does it imply? The organic content is part of the soil of the solid phase. What does it imply? If organic content is high, what can it do? Where else do you use organic solids? Any application that you are aware of? The? Agriculture. Something more common, more. What do you use in agriculture for? That is a different application. With reference to water, do we use organic solids for anything? Maybe in water treatment? Activated carbon, what do you use it for? Treatment of water. What treatment means? What exactly? Adsorption, which means what is a more general description of adsorption? If I do not know the word adsorption, how can I describe it? It what is adsorption? Removal of? Yeah, it's removal of, no. Activated carbon is used there for a specific reason. Why do you have carbon? So, we looked at it in the organic property of organic carbon. It is a large backbone of carbon, so it likes carbon. So, if organic content is high, organic carbon likes other organic chemicals. This is true. More or less, if you have a large organic content, it is likely to attract organic compounds. Okay. So, you are likely to find that if the organic content is high here, you are also going to find this in the same direction. A large amount of organic chemicals are also likely to go to the forest soil than this. So, this leads to more accumulation. Then we have a problem. If you want to describe Ka32 for a particular chemical, I have to then go and get the organic content of all these things, and then I have to do an experiment to actually get what is the. So, I can't have a uniform property. I can't say Ka32 of a chemical between two particular soil. Ka32 of a chemical itself I can't classify, because I need to know about the organic carbon content. I need that also information I need. So, this is we will use this in calculations, but this is not you can't use it as a property of a chemical. But from this observation, what people have looked at is that I can write this Ka32 as Wa3. Just now we have also determined that organic carbon content is different. So, we will write this as, instead of Ka32, we will write this as Ka organic carbon divided by, yeah. So, we will write it even more expandedly. We will say m of A divided by m of OC, m of OC divided by m of 3 divided by, if I break up the numerator into two terms, here we are writing this as Wa3. Wa3 is m of A by m of 3. If I write that in terms of this, so this first term here is the second term here is the content, organic carbon content. It is the amount of mass of organic carbon divided by mass of the solids. Okay, so we will give this, we will call it as fractional organic carbon, and this term here then becomes, it is the mass of organic of chemical A over the mass of organic carbon. So, okay. This number here becomes a little more normalized. So, what it says is, if I know what the organic carbon is in general, I can now say that the adsorption of a particular chemical, partitioning of a particular chemical on organic carbon with reference to water should be more or less the same. So, I am removing this FOC out of the equation, I am separating it out. So, what I will do is I will instead write MOC, MA by MOC into 1 by rho A2. This makes it as WAOC by rho A2 into FOC. If I do this, this number here is a normalized partition constant. So, it does not depend on the amount of organic carbon, it depends on the type of organic carbon. Okay. You understand? Clear? So, here again we discussed in class that there is likely to be variability in organic carbon itself, but then collection of a lot of data, people have figured out that the organic carbon has a certain range in which it behaves. So, the composition does not change a whole lot unless there is exceptional conditions. So, people have measured this. So, they have measured the Ka32 using experiments like what we have described here, and then they have broken it up. They have also measured the organic carbon and they have normalized it. They have separated the organic carbon content and the ratio of the WAC over rho A2, and this number, this quantity WAOC by rho A2 is now called as KOC, it is KAOC. KAOC2 is our definition, but this is KOC is a generalized term, it is there in literature as KOC. KOC is the partitioning of a chemical between organic carbon and water. The assumption that organic carbon is the same throughout the entire world, which may or may not be true. This is the first exercise that you have to do, is I will ask you to go and get organic carbon log KOC for different chemicals. You will see the range of KOCs. It is not one number, it will vary, and it varies for a good reason. It varies for the reason that we just mentioned. It need not be the same everywhere. Depending on the origin of organic carbon, this composition will change, and therefore the number will also change, partitioning will also change, and it is more complicated than what we give, but this is a convenient methodology to do this. So, KOC is a physical property that can be listed if we assume that organic carbon has a certain property. So, when people measure organic KOC of a new chemical, you need a reference, right? Where do I get organic carbon from? I have to get it from, I can get it from India, I can get it from China, I can get it from the US or Europe, Africa, anywhere. Organic carbon, which means I get soil from different places and I extract the organic carbon and then use it. So, people have standards. So, there are standards to which you measure KOC of a particular chemical, you have to use those standard matrices. So, once we have mentioned in the last class called humic acid and fulvic acid and all that. So, we use one of those. So, there are standards available in the market that you can buy, and you can report KOCs based on that. So, when you look at experimental data for KOC, people will mention what is the organic carbon that they have used. They have used one type of OC or naturally occurring OC or a synthetic compound which mimics the organic carbon. All these are possible. Okay. So, this log, and we usually represent it as log KOC, because KOC is a big number, and you can imagine if I have a few milligrams of organic carbon, the solubilities of a lot of these chemicals are very small, but they are organic, they like organic phases, so they all will go there and they will stick there. That is the reason why we use them as adsorbents, because their KOC is very big. The partitioning from water to the solids is very high. That is the reason we use them as adsorption and that is why soil is considered to be a naturally purifying medium, because while before it goes to groundwater, it has to go through all the layers in which there is organic carbon, and that will absorb a lot of these chemicals. And so, this number is big. So, instead of writing 10,000 and 20,000 and all that, they will just convert it to log of KOC. So, again the KOC has units, so same units as that. So, the nomenclature, the convention is KOC is usually in liters per kilogram. KOC has units of liters per kilogram, because it is coming from milligrams per kilogram and milligrams per liter. This is the concentration units of any chemical on solid, and this is the concentration unit of chemical in water. So, this is usually therefore you cancel this, you get liters per kilogram. So, that is general, this is convention. When you see only log KOC, if you say log KOC of 4, it means KOC is 10 raised to 4 liters per kilogram, unless otherwise specified normally. Sometimes people will just give you the KOC and different units. So, 10 raised to 4 liters per kilogram is 10 meter cube per kilogram. They will give you 10 meter cube per kilogram, and that is also valid. But if there is a mention of only log KOC, then it is assumed that the units of KOC are liters per kilogram. Okay. So, in association with the log KOC, so we have now properties of we have aqueous solubility, we have vapor pressure, we have Henry's constant, we have log KOC. So, in association with log KOC generally gives you the affinity, the tendency of a chemical to bind to an organic phase. This is a general assumption. Yeah. There is a larger implication of this. So, before environmental scientists came about and invented log KOC, because this pertains mainly to soil and sediments and all that. In pharmacology, in toxicology, people look at this number differently. Okay. What they look at is if you are eating a medicine or a poison, or how toxic a particular material is when you through different routes, inhalation or oral route. They look at the binding of this particular chemical, its accumulation in the human body, in your tissue, and this they call as bioaccumulation. This bioaccumulation also is determined by looking at the theory. There is that most of the blood and all that, or the food goes in, it gets digested, it is going in more or less an aqueous solution, and it is partitioning between different portions of the tissue, okay, as it is going. So, if a chemical has a very high partitioning between water, a water based aqueous based system, and a very high organic lipid, tissue is considered to be a lipid based this thing, fats and tissue and all that. So, people look at that partitioning, and so they can have different numbers. We can have Ka, some tissue and water. Okay. They can do it at different levels. They can take, say, some animals, they will just dump the animals into water, put a chemical, and after a point in time they will see how much of chemical has gone into the animal, into a fish or into something else. That is one bulk thing you can look at. Or you can take a particular tissue and you can probe which part of the tissue, how much accumulation is happening on the tissue itself. So, this bioaccumulation factor is also based, it is just like the log KOC, it is a ratio of two concentrations. So, in this context people have what is called as KOW. Now, this is a normalized number. Instead of using lipids, they use octanol. Octanol is used as a surrogate for lipids. Okay. So, it is an octanol water partition constant. Okay. So, this is KOW equals, now we will just write it as rho A octanol versus rho A water. This is how it has been determined originally. So, they do not use WA, they use rho A for some reason. But octanol is a liquid when you are doing the test outside, but in the human body, in the body tissue is solid. Okay. So, measurement of that is very difficult. So, what people have done is they need a common basis to which in which they can estimate accumulation factor. So, the KOW or octanol water constant, this octanol is considered to be a good surrogate of the lipid. So, which means it is a reasonably long chain, and then it has an OH group, it has 8 carbons and then it is OH group. So, it looks like the organic carbon. It looks like organic carbon. Organic carbon we said is a long chain hydrocarbon with polar groups at the end. So, octanol is not that long, but some number. So, they have chosen it by on some basis based on the analysis of the lipids and how they. So, it is not the actual number that will be there in the human body, but it is notional. It gives you a scaling, it gives you some kind of a comparison of what? What does it give you? So, if you look at log KOC and log KOW, both of them will give you a quick idea. If you compare the log KOC and KOW of different chemicals, organic chemicals, it very quickly looking at the values you can tell whether this chemical will bind to an organic phase or will stay more in the water, whether it likes the oil, likes the organic carbon or likes the water. So, this we come up with another term called hydrophobicity or hydrophilicity. Hydrophobicity means it does not like water, or hydrophilicity means it does not like the carbon. Okay. So, this is a scale of hydrophobic behavior. if a chemical is hydrophobic, which means high KOC or KOW, which means highly hydrophobic. For relative things, there is no absolute term for hydrophobicity, there is no absolute, this is relative, because one chemical versus another chemical, one of them will, or you can say that a chemical which has a log KOC or KOW of 1 versus log KOW of 4, which means this is 1000 times more than that. So, this one will accumulate 1000 times more than that. So, they will do this on the basis of, it also gives you some idea of how much hydrophobicity can be, if you want to design a particular chemical, especially for, this is used a lot in pharmacology. As we discussed, that pharmacology looks at how much of accumulation in the body. The medicine, you need the medicine to go and bind to a particular site in order to work. So, if a chemical is not at all hydrophobic, it is hydrophilic, then it will not accumulate anywhere, it will go out, it will pass out, body will send it out without any adsorption, any accumulation. So, there are various applications to this, both environmental as well as this thing, but this property of KOC and KW is used as an index to see whether, just quick reference, right. So, you can look at all these properties and say where the chemical is going to be. If I look at all these properties, and I can quickly give you a very qualitative view of, this chemical is likely to be more in air than in water, or it will not be in water, it will be in the sediment soil, it will come out very slowly, which means you can make very quick decisions as to where your attention should be, your focus should be on remediation or treatment or whatever that you need to do, subsequent decisions to it. So, these are important properties, and most of the chemicals that are of concern to us, these properties are listed. So, these last two pretty much, except the last 4, most of them is organic chemicals is the focus. The first one you have both organic and inorganic. The partition constant Ka32, we are worried about it from both inorganic and organic, both of them will partition, but the KOC theory only applies to organic chemicals, it does not apply to inorganic chemicals. Okay, we will talk about inorganic chemicals tomorrow, what happens to them and how does the Ka32 change for that, but you can't generalize it like this, you still have to, find out other set of conditions, which is not very easy, you have to do it very site specific, and there is no generalized theories based on for that. Okay.